There is fresh evidence of a massive planet that may have come into existence due to past planetary collisions. A team of astronomers from different countries have found a planet with a size similar to Neptune that has an unusual density comparable to that of steel. The scientists hypothesize that this exceptional composition could have been caused by a significant collision between two massive planets. The mass of TOI 1853b is nearly double that of any other planet of similar size within our knowledge. Furthermore, its density is exceptionally high, indicating that it is comprised of a greater percentage of rock than what is commonly observed at its scale. Today, a report was published in the journal Nature detailing the findings of a study conducted by a team of scientists led by Luca Naponiello from the University of Rome Tor Vergata and the University of Bristol. According to their research, the absence of water and lighter atmosphere on certain planets can be attributed to planetary collisions. The study suggests that these massive impacts would have caused the removal of the aforementioned elements, leaving behind a multitude of rocks. Dr. Phil Carter, a co-author and senior research associate at the School of Physics in Bristol, provided a thorough explanation. Our solar system has presented us with compelling proof of high-energy collisions between celestial bodies, such as the formation of the Moon orbiting Earth. We also have some credible evidence from a limited number of exoplanets. The variety of exoplanets within their respective planetary systems is vast. Although many of these planets do not have a counterpart within our own solar system, they often share similar characteristics with masses and compositions ranging between that of the rocky planets and the ice giants, Neptune and Uranus. Our study aimed to create models of giant impacts that are extreme in nature. These impacts have the potential to eliminate the lighter atmosphere and water ice components from the original planet, resulting in the high density that was observed. Based on our research, it appears that the creation of TOI 1853b, as it currently exists, would require two key factors. Firstly, the original planetary object would have to possess a significant amount of water. Secondly, an intense impact at a velocity surpassing 75 kilometers per s would have to occur in order to achieve the observed properties. The discovery of this planet offers further proof of the widespread occurrence of colossal impacts during the formation of planets in galaxies across the universe. This finding serves as a bridge between theories of planet formation that are rooted in our own solar system and the creation of exoplanets. The discovery of this extraordinary planet also provides fresh perspectives on the development and transformation of solar systems. Jingyao Dao, a co-author and postgraduate student, expressed amazement at the planet's characteristics, stating, "It's truly remarkable." Typically, planets that have a comparable amount of rocky material in their composition transform into gas giants with densities akin to water, similar to Jupiter. According to our research, TOI 1853b possesses a density higher than steel, despite being the same size as Neptune. This peculiar phenomenon can be explained by the occurrence of highly vigorous planet-planet collisions during the planet's developmental stages. As a result of these collisions, a significant portion of the planet's lighter atmosphere and water were removed, leaving behind a planet with a higher density and an abundance of rock material. The team has a plan in place for comprehensive observation of TOI 1853b to determine if there is any remaining atmosphere and to scrutinize its chemical makeup. After conducting research on the subject, Associate Professor and co-author Dr. Zoe Leinhardt reached the conclusion that the concept of extreme giant impacts had not been explored previously, as it was not an anticipated scenario. She also stated that there is an ample amount of work that needs to be done in order to enhance the material models that are used for simulations, as well as expand the scope of the extreme giant impacts that are modeled. The computations were executed through the computational resources provided by the Advanced Computing Research Centre at the University of Bristol. The funding for this project was provided by the Science and Technology Facilities Council, STFC, and the China Scholarship Council. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.